This is the one where we actually do the kind of poisoning that's really fun. We're going to poison real images. So we're going to go back to the MNIST dataset, which is those handwritten letters. So we go to here, and let's get rid of this old stuff. Move to trash. Yeah, I don't care. I'm just going to abandon the calculation in progress. All right. So you get a new notebook. Okay. So this is the commands that downloads the secml library. Too many sessions. Well, let's terminate sessions. Terminate them all. Terminate other sessions. There we go. There. All right. Kill them all. I don't have anything happening that I care about. There we are. All right. This is pretty awesome that Google gives us all this computing power for free. I really appreciate it. So there it is, downloading the secml library and installing it. And then it's going to download the MNIST data and load that up, which is those 70,000 images of handwritten numbers. All right, and there it is, getting a bunch of files that are the portions of that data and unzipping them. And it's done. All right, so we move this down so it's easier to flip back and forth. All right, so now we're going to select a small set of samples. We're not going to use all 70,000 images. We're only going to use a small set to make it the calculation faster. What we're going to do is we're only going to use 5s and 9s, nothing else. And we're only going to use, the training set is going to have 100 samples, and something called the validation set, which I don't really understand, it has 500 samples, and the test set has 500 samples. So we're only going to use 1,100 samples, and they're all going to be either 5 or 9. That's what this is going to do. So you run that, so you get a training set, which is 100 rows, each row containing 784 pixel values, so 100 images, and this next validation set has 500 images, and the test set has 500 images. So that's what we're going to use. All right. And next, we're going to view some of these samples to see what they look like. So this is going to print, I think, the first 8 of them. All right. So there's the first 8 of them. So the right answer is on top. This should be a 5. This is a 9. That's a 5. That's a 9. And they're all either 5 or 9. So that's the data we're working with. All right. So now we're going to train a classifier. This is a binary classifier to tell the 5s from the 9s. So it's the same thing we've done before. This is going to do a fit on the X and the Y. And then it's going to use the test data to see how accurate it is. So since we're using so few models, it's extremely fast. It just took less than a second. So it trained it, and the accuracy is 93%. So, all right. So now we have a model we can examine. And now we're going to perform an evasion attack. It's 93% accurate, and this is going to use the first 25 images, and we're going to poison those images using one of those gradient descent careful poisoning attacks that takes an existing image and modifies it to make it confuse the model. So this is going to poison 25 images, and then it's going to show us the accuracy of those 25 before and after. So before the attack, all 25 are correctly predicted, and after the attack, only 12% of them are correctly predicted. So the poisoning was extremely effective. And the most interesting thing is to see what they look like. Here's what they look like. You can demonstrate, you can show the poisoned and original images here. It's evasion. This is called evasion. Changing the training set is called poisoning. So these are malicious images that evade detection. And here they are. This is the original 9. This is the modified 9, which is now incorrectly identified as a 5. The red letters mean it incorrectly identified the image. I think for the video, I'll just zoom in. We don't need to see them all. All right. So I'll try to make it the right size. Okay. So this is the original set. They're all green because they're all correctly identified. Here's the evaded set, and they're all being misidentified. So adding just these little blurry bits here made it think that was a 5. Adding these little blurry bits here made it think that was a 9. This one it thinks is a 5, which is, it really looks like a 9 to a human. And this is the fundamental problem with machine learning. Small changes in the input that do not really represent a significant change when observed by a human will fool the model. And this probably applies to all machine learning. There are people trying to figure out why this happened. And as far as I could tell from the stuff I read, this remains an unsolved mystery in machine learning exactly why this happens. But unfortunately, you can have a model that is extremely accurate, like here it identifies 25 out of 25 correctly, and yet small evasions will cause it to be very inaccurate. So that's a sort of fragility of machine learning models that is important to understand. And so I think that's all I need to show you here. There's just a flag to turn in for this one, and I'll probably add more to this project later. But anyway, that's what I wanted to show you. That's as far as I've gotten with these machine learning models.